Hello, how are you? Today we are gonna do chemical kinetics. Do you know what is that? Do you know that? What is the chemical kinetics? Thank you so much, Mayat. I'm fine. Yes, today we are gonna explain that these chemical kinetics and what is that? What is uh, purpose of that subject, and so on. Yes, the question. What is that? Do you know what is chemical kinetics? This chemical kinetics about what? Some students are coming still. Only 8 students. I think the last weeks always do that, and students getting less. Yes. Are you there? Abdulbari, Bihter, Erik, Ertuğrul, Moyat, Rojat, Yusuf. Yes, what is that? The chemical kinetics. Do you ever heard that this chemical kinetics from the high school? I think you didn't ever heard. Actually, the chemical kinetics about the reactions rate, reaction speed rate. Speeds are very important for the chemical kinetics. For example, if we have some products, these products getting sometimes some at the times, for example, hydrogen peroxide decompose while hydrogen peroxide decompose. It has been sometimes and the products have getting water and oxygen, and these are the products, and these products produce for example 5 minutes like that. The chemical kinetics learn us these information about that. For example, look at that picture. That picture tells us actually this reaction occurs at room temperature, stable room temperature. Ammonium dichromate decomposed here very rapidly once ignite. Okay, and the rates of chemical reactions and the effect of temperature, these rates are several key concepts explored in that chemical kinetics, and produce some here produces some products like that is nitrogen gases, water gases, and chromate solid one here, the chromate, and that reaction will be at it is what's that means the ignited here, and actually some heating needed here for the reaction. And for example, for the chemical kinetics, for example, some of that for chemical kinetics, first of all, rocket fuel is designed to give a rapid release of gases products and energy to provide a rocket maximum thrust. and the other one milk. For example, milk is stored in a refrigerator to slow down the chemical reaction that cause it to spoil. Okay, if you put this milk at room temperature, the chemical reaction occurs rapidly. But if you put that in the refrigerator, these chemical reaction occurs slowly, and this is the chemical kinetics. This is about the chemical kinetics. And then the third one, current strategies to reduce the rate of degradation of the ozone layer. Try to deprive the ozone consuming reaction cycle of key intermediates that come from chlorofluorocarbons. And the other one, catalysts are used to reduce the harmful emissions from internal combustion engines that contribute to smoke. All of these examples illustrate the importance of the rates of chemical reactions. For example, how fast a reaction occurs depends on the reaction mechanisms by step molecular pathway leading from reactants to products. So the chemical kinetics concerns how rates of chemical reaction are measured. Okay, how rates of chemical reaction are measured, and then chemical kinetics concerns how they can be predicted and how reaction rate data are used to deduce probable reaction mechanism. And the other one, the rate of chemical reactions. For example, here the rate or speed or refers something that happens a unit of time. For example, look at this reaction. This reaction tells us the iron 3 plus and tin 2 plus occur reaction, and then this is the redox reaction. You know that iron 2 plus and then tin 2 and then tin 4 plus aqueous solution. For example, here the aqueous solution also, and 38.5 seconds after the reaction starts, and molarity of iron 2 plus is found to be 0.001 molar. And then here, first of all, the initial time, for the initial time, iron 2 plus molar rate is only 0 because we have no any iron 2 plus. During this reaction occur, the period of time, this is delta T means 38.5 seconds. The change in the concentration, this is the iron 2 plus. We can say that this delta iron 2 plus concentration equals 0.001 molar minus 0 that equal the 0.001 molar. And this average rate at this iron 2 plus is formed in this interval is the change in concentration. This is divided by the change in time. Don't forget that the rate of formation of these ions or some molecules always will be like that. This is delta and then concentration of the products or products or reactants we can write here, divided delta T, this is the change in time, and then you will find the rate of formation for iron 2 plus. And you will do that the same thing for tin 4 plus, the same thing because the reaction time the same, the delta T change in time the same, and but concentration of 4 plus tin different. What is that? Do you think that about that? For example, if I want to write the rate of formation of tin 4 plus, I will write here, what is that? I will write here, yes, the delta T. What I said, change in time, the same thing, yes, but delta concentration of T4 plus is different because look at here, the chemical reaction, and then what do you think about concentration of tin 4 plus? What do you think about? Yes. For example, Doğaldem. Welcome to here, Doğaldem. I will. It is the first time I see your name here. Bihter, say something. Yes, 0.005 molar. Yes. Why Bihter like that? Why? It is half of concentration of. Yes, we can say like that because the iron 2 plus concentration, or we can, this is molarite or or we can say mole. Yes, this is only half of concentration than the iron 2 plus. Thank you so much, Eric and Bihter. Yes. This is the explanation of the rate of formation tin 4 plus. How has the concentration? Yes, I am asking to you for the tin 4 plus. Yes, this is only 0.0005 molar minus with 0 equal like that, and will be this rate of formation tin 4 plus will be like that. This is molar divided seconds. Don't forget that. And also, for example, we can give some example of that. A car traveling a car at 60 mph, for example, covers distances for 60 miles in 1 hour. For chemical reaction, the rate of reaction describes how fast the concentration of a reactant or product changes with time. Okay, don't forget that. Also, I said that actually the delta means, yes, the delta change final volume minus and the initial volume. Don't forget all of these volume. Yes, here actually the same reaction, the redox reaction, and if we want to write for the iron 3 plus, we write here the negative because this is the reactant, and reactant always consumed, and so we write here negative and divide at the same time, and you will find the change in concentration like that. That means the negative means it these ion consumed. Okay, the quantity above the average rate of change iron 3 plus concentration in this interval, it is a negative quantity because this is decreased with the time. This is iron 3 plus, and the rate of disappearance of iron 3 plus, okay, disappearance because consumed that, we write here negative, and write here the same molarite, but only you write negative one. This is that will be negative, and here the negative you write here only negative. I think that will be that would be here the negative one. Okay, don't forget here. This is yes, this is true, but here there will be a negative sign. Yes. And the rate of reaction always will be like that. The International Union of Pure and Applied Chemistry, you know that this is the IUPAC, recommends that we use a general rate of reaction. Okay, general rate of reaction. This is for the hypothetical reaction represented by the balanced equation. You will write here like that. This is negative one because the A consumed. This is reactant. Reactants always consumed. Okay, while reaction occur, these reactants A and B always consumed, and G and H always produce. And so we write here negative 1 divided A. This is the coefficient, and that means the mole or molarite, we can call that. This is the delta concentration of A, and divided delta T. This is the time, delta time, and equal that one for the B reactants. And don't forget to write negative here and negative here. Okay, don't forget here to write. And the other one for the G and H, this is the products, so you have to write here the only 1 divided G coefficient and 1 divided H coefficient, and you will write always for the divided with delta T, delta T, delta T, and delta T. This is the important thing. These are the what's that? These are the reactants, and these reactants always consumed decreases, and the other ones H and G and H always produces. Okay, always increasing, like think like that. And rate of reaction, if you write if you want to write for the other redox reaction, you will write like that: rate of reaction negative 1 divided 2 delta concentration of iron 3 plus divided delta T, delta time, is equal with, for the tin you will write, and then you will write the products. For the products only 1 divided 2 delta concentration of iron 2 plus divided delta T, but here there is no any coefficient, because here, look at here, there is no any coefficient for the tin 4 plus and tin 2 plus. So you don't write anything here, only you don't forget that for the negative or positive sign. Yes, here, suppose that at some point in the reaction for A, B, and 2C and 2D, if I ask you about chemical reaction, I won't write any coefficient, but here, yes, I have to write here, because A and B, what is that? What is this molecules and compounds? You don't know anything about that, so I have to write here the coefficient. But if I ask you about the molecules here, for example, hydrogen peroxide, or I will write this is glucose, and this is the, for example, oxygen one, and we have carbon dioxide products and water product. I won't write any coefficient here. First of all, you have to check your chemical reaction, and then it is needed some coefficient. You have to write that, and then you have to calculate. Okay, you don't forget that. This is important thing for the exam. For the beer, they ask us the B concentration is 0.9986 molar, and that 13.20 minutes, okay, minutes later, this is the minute one, okay, and then they ask us molar divided second. Don't forget that here the minute and they ask us seconds. So be careful here. First of all, if you want to first here, you can convert that, or if you first of all, if you want to calculate all of these calculation, and then you can convert. Okay, it is up to you. This is minutes later. The concentration of B will be 0.9746 molar. What is the average rate of reaction during this time period expressed in molar divided second? Don't forget here. Okay, be careful here. The units always, I will say you, I said always to you, the unit always so important for the chemistry. Yes, here, first of all, the differences between concentration of B molarite, first of all, you have to find that. Delta B, what is that? After some minutes, you get some concentration of B. This is the 0.9746 molar minus with the first concentration of A. That means you have to find negative because this is the decreases and this is the consumed for the A concentration, and this at this time. Okay. First of all, you will find that. You will find the delta B concentration, and so after that you will step this average rate of reaction. You will know that they ask us what is the average of reaction during this time period expressed in molar divided seconds. If they ask us for the B, so you have to write the rate of reaction for the B one, and so you write here B is the reactant, and reactant always decreases and consumes, so you have to write it first of all negative. And you will write 1 divided, what's that? This is the coefficient. You have to write here the coefficient and multiply with the delta B concentration. You know that from here. From here, you know that, and then divided delta T. Delta T means this is the differences or delta time, and you put all of these values here. That values you put here. Just that value you will put here, and that value you will put here, and then calculate. You will find that one. But here you will find only minutes, but they ask us only seconds. So you will then convert that. Here you will convert. What is that? This is divided. That means that divided 60 seconds, and you will find like that. So after the 13.20 minutes later, the rate of reaction will be only 1 second consumed here, 1.01 multiplied with 10 negative 5 molar, we can get it. For chemical reaction will be like that, and here also I also, this is clear because only you have to know that to write average rate of reaction, and you will find here, and you know here. You put all of these values and then calculate, you will find the result of this example. Is that clear? I think clear. I will pass here. Clear or not clear? 17 students tell something. Clear. Thank you so much, Bihter. We will do this lesson together. The others not here, I think. And this maybe affects your yes, this is your homework. Yes, here at some point in the reaction, they give us some reaction, chemical reaction. There is no any compound, only A, B, C, D. And here, that one, this is the minutes again, and the gas molar divided second again, same thing. And that one, please solve that problem. Study your exam. Do you know that what is your date of exam date? You know that? I think not 14th, yes. 16th June. Yes, yes, that's right. Bihter. Who is Süleyman? Süleyman, this is not, yes, this is not true. Okay, 16th. Okay, thank you so much, Bihter. And also, I will send an email about that. Okay, Süleyman, okay, I understand. Effects of concentration on reaction rates, the rate of law. The terms here, like that, term concentration of and B, reaction rights, you know that. This is here, that M and N here. Small one. Positive whole numbers, generally we will use that. Positive whole numbers. Sometimes these M and N, they may be zero, fractional, or negative. They must be determined by experiment and or are generally not related to stoichiometric coefficients. Okay, don't forget that. And one of the goals of in chemical kinetics study is to derive an equation that can be used to predict the relationship between the rate of reaction and concentration of reactants. So we can call that this is the rate law or rate equation. Okay, rate law or rate equation. Rate of reaction will be rate of reaction will be like that, and here the reactants, always we write here the reactants, and this is the constant one. T is the constant, like that, and it is not the coefficient about reaction. Yes, here some explanation of the rate law. The term order is related to the exponents in the rate law, and is used in two ways. First of all, if M1, we say that the reaction first order in A. Okay, if N2, the reaction is second order in B, and so on, like that. The first one, the first way, the overall order of reaction is the sum of all the exponents, m plus, n plus, etc. like that. The proportionality constant T relates the reaction of the rate of reaction to reactant concentration, and it is called rate constant. Okay, the rate constant always is up to the chemical reaction. This is the special for chemical reaction. Its values depends on the specific reaction, the presence of a catalyst, if any, and the temperature. The larger, just a I'm sorry. Yes, we state here the rate constants always depends on the specific reaction. Don't forget that, and the presence of a catalyst and the temperature important and changing that one. In order of the reaction establishes the general form of the rate law and appropriate units of key. This is the important thing. Yes, here with the rate law for a reaction, we can say like that: the calculate rates of reaction for known concentrations of reactions, derive an equation that expresses a reactant concentration as a function of time. Don't forget that this law for a reaction. Yes, here zero order reaction. Zero order reaction means sum of the exponents. This is n plus n is equal for the zero. Okay, as an example, let's take a reaction which like that. This is for the A is the product. A single reactant A decomposes product. Here the A only reactant, okay, and then give us some products. If the reaction is zero, the rate of is here will be like that, the rate of reaction. Key, this is the constant concentration of A, and M will be zero for that reaction. That means this is zero order reaction. And the key, that one, this is the constant only. If the zero here concentration, that will be the concentration of A concentration will be only 1. So the rate of reaction will be only constant. This is the key. And other features of this zero order reaction will be the concentration time graph is a straight line with a negative slope. And the second one, the rate of reaction, which is equal to key and remains constant through the reaction is the negative of the slope of this line. And then the last one, the units of key are the same as the units of the rate of reaction, mole divided liter time or mole divided liter. That means the molar divided second. And we have some graphs for zero order, first order, or second order, but this graph not important, only explanation of that the zero order. You should know only where is come from for the zero order or the others. Here, for the zero reaction, A is the reactant and give us some products, and A for A concentration for the first time, zero time, the concentration of that decreases with time. This is the time, and this is the A concentration will be like that. And what is the formula of zero zero order? This is time of A concentration equal negative key multiplied with time and plus first the zero time of concentration for A. This is the important thing about important thing to solve this problem for the zero concentration, zero order concentration. Okay, this is the important thing. This is the that formula is very important. This is the where is the come from here. This formula comes from this. Let's say this is the graph. Okay. What about the first order reaction? First order reaction has a rate law. Some of the exponents, for example, m plus n. M plus n equal only 1. Practically common type of first order reaction, and the only type we will consider that is one in which a single reactant decomposes in the products. For example, here hydrogen peroxide in aqueous solution decomposes with water liquid and oxygen gases. And if you want to write here rate of reaction, we will write here will be key constant and concentration of hydrogen peroxide, and up only here will be only 1, and that means the first order reaction. Okay, if we want to write this reaction with the graph, and that will be like that for the first order reaction. Again, the same, the rate of reaction will be like that. Negative delta concentration of A divided delta T is equal constant concentration of A. We can obtain that integrated. This is very important. While we do that, this integrated, we will use some graphs, and then we get some formula for the first order reaction. Applying the calculus technique of integration, here we have ln, we will use that, ln T, the time of concentration A divided the time, what's that, this is 0, the first concentration of A, equal the negative key T, or we write here like that. Okay, don't forget that this is very important solving this problem about the first order reaction. Okay, this is the time of A, and this is the first concentration of A. And this is equation of straight of line in the graph. This is the Y, and this is the MX, and this is the B1. Okay, this is about the graph only. Let's come from here. It's come from the line or the graph here, like that. Yes, doing an example about that. Here, hydrogen peroxide aqueous solution, initially at a concentration of 2.32 molar is allowed to decompose. What will concentration of hydrogen peroxide be at the time 1200 seconds? Use that one, the key. Okay, the key always constant, and that will be given to you for an exam. For this first order composition, and they say to you, oh, this is the first order reaction. You know that what is the formula for first order decomposition? Here will be like that. Okay, ln concentration time of hydrogen peroxide, and this is that will be negative kt, and ln the first time, the initial time of initial concentration of hydrogen peroxide. First of all, you have to write these values, given values. Here, second, not any problem to convert that. And this is initial hydrogen peroxide concentration, right? And write all of these values, and then you will find that molarite, the time concentration of hydrogen peroxide. Check here, 0.967 molar at that time, but here the first time 2.32 molar. Yes, that will be decreasing here. Okay, decreasing here. So this is the true value of the time concentration hydrogen peroxide. Only you will put these values and then calculate that one. Don't forget that this is important thing, because this is ln. You will find this is the ln. Be careful here. You will find some calculator with it. you will do that. Yes, I think this is clear. I will go on. Here, this is your homework again. They said us this is the first order, and this is the first order. You know that the first order formula, what is that? You will use the ln one, and you will do only what you put in the formula and calculate. Yes, let's doing the second order reaction. Second order reaction here has a rate law with the sum of the exponents m plus n equal only 2. And the rate of reaction will be like that. Key concentration of A 2. And again, our primary interest will be in the integrated rate law, that is derived from the rate law. This proves to be equation a straight line graph. Okay, if you want to put all of that one, the straight line plot for the second order reaction will be that one. Okay, 1 divided concentration of T time for the A equal KT plus 1 divided A, the first concentration. Okay, that formula comes from these graphs, but this graph only for the showing to you. This is not important how to this is coming here. Yes, here I can't. Sorry. For the half-life of the second order reaction A products, we can substitute like that. This is T. The half-life will be T1 divided 2, and A concentration will be like that. If you want to write here for the half-life of the second reaction for A, we will write T1 divided 2 equal 1 divided key constant 0 of concentration will be like that. The half-life is not constant, okay? Its value depends on the concentration of reactant at the start of each half-life interval. Don't forget that, because the start concentration is always 1/2 that of the previous half-life. Each successive half-life is twice as long as the one before it. Okay, don't forget here for the half-life. Yes, here the summary of reaction, chemical kinetics reaction. Here, let's briefly to review what we have learned about rates of reaction, rate constants, and reaction orders. Although a problem often can be solved in several different ways, these approaches are generally most direct. What are they? First, to calculate a rate of reaction. When the rate law is known, use this expression, okay? The rate of reaction. Use of that, the key concentration of A and concentration of B. And that one, the second one, to determine a rate of reaction. When the rate law is not given, use here, but you don't use the graph line, only this is the information about that, okay? Because you won't use some graph of for the 0 or first or second order. Eric, say something. Half-life to differ for first and second order of reaction. Only we will do that half-life for the second order reaction. Okay, only you know that. The other is not important. And the other one, the third one, to determine the order of reaction, use one the following methods. What are these? Use the method of initial rates if the experimental data are given in the form of reaction rates at different initial concentration. And the other one, these are some about the graph. Find the graph of rate, data that yields a straight line, and the test for constancy or the half-life. And the last one, substitute rate data into integrated rate laws to find the one that gives a constant value of key. And the fourth one, to find the rate constant key for a reaction, use one of the following methods. What are these? This is about the generally graphs. Obtain key from the slope of a straight line graph, and the other ones to substitute concentration time data into the appropriate integrated rate law, and the other obtain key from the half-life of the reaction, that one. The last, I think, to relate reactant concentration and times, use the appropriate integrated rate law after first determining for key. This table actually tell us this is summary of all of that laws, the 0, first, and second laws. What are these? For the 0 order, the rate law will be always constant. And integrated rate equation, this is important. This integrated rate equation, very important to solve problem, because when we solve the problem, while we are solving the problem, we will use that integrated rate equation. Okay, not the rate here or not the others one. We will use that integrated rate equation because we will use this sum graph and solving some problem. And this is for the first, not first, for the 0 order. 0 order will be like that, and solve that problem from this formula. Straight line will be like that. Straight line will be a concentration and time, and the key negative slope, and units of key will be molarite divided seconds. Okay, half-life will be like that. This is half-life only. You know, like that. Okay, this is not important. I think I won't ask you about the half-life, because this is complicated, because if I want to explain that one, this is so complicated. This is the others one more important for you. For the first order, the rates will be key multiply with the concentration of A, and integrated rate equation will be like that. This is that ln come here, and straight line will be for the Y, I think ln A concentration, and the X line will be time. Always the X line will be time. Okay, for the graph first, 0, or second, or third order. And the key negative slope and units of key will be only 1 divided second, and half-life will be like that. And for the rate, for the second rate, equal key concentration of A2, and integrated rate equation will be like that. This is actually the same, but there is no ln here and there is no ln here. Maybe that's similar with that 0, but here 1 divided. Okay, divided only, and here there is no any negative one. A straight line will be 1 divided concentration of A, and I said to you, X line always will be time, and key slope and the units of key liter divided mole second. This is the molar, but this is not molar. Don't forget, this is only 1 divided molar. Okay, 1 divided molar means. Yes, this is the summary of chemical kinetics table. Okay, and the last one is effect of temperature on reaction rates. Only you know that this is the key constant. You know that this is the a reactant, and this is the Arrhenius constant. I think EA, Arrhenius constant, and R, this is the constant, the gas is constant, and T is the temperature. And Arrhenius demonstrated that the rate constant on many chemical reactions vary with temperature, and that expression will be like that. If we want to logarithm like here, if there is some temperature, for example, the first temperature or second temperature, this key constant will be changing, and you have to write here the key 1 and key 2. So Arrhenius, this is the Arrhenius constant, this is the R constant, this is generally the gases, and this is the temperature. You will write here. This is LNA, this is reactant Ln, concentration, I think. This is will be like that. This, the effect of reaction on the rates, generally practical experience, we expect chemical reaction to go faster at higher temperature, but sometimes vice versa. To speed up the biochemical reactions involved in cooking, we raise the temperature, and to slow down other reactions, we lower the temperature, as in refrigerating milk, for example, milk, to prevent its from souring, like that. Yes, for that week, that's it. If you want any question, you can ask. And also, today is the last day. Submit your report to Bihter. You know that. This is after today. I won't accept your reports. Okay? Do you have any question? Yes? Are you there? The lesson is finished. Thank you so much, Bihter. See you soon. Bihter, you will send to me email your reports. Okay? See you. Okay, see you next week. Take care of yourself. Thank you so much, Bihter.